Alright, so finishing up the last unit in the notebook here. Solenoid, radius r, n turns per length. Remember, little n different than big N. Little n is the total turns divided by the length. Don't get those confused when you see them in formulas. Current I increases at a rate. Use Faraday's law to determine the electric field at point P and Q inside and outside. So we've got a magnetic field pointing to the right. We know the magnetic field is pointing to the right. The current at the top is going in to these wires, and then the current's coming around and coming out the wire. So if you were to curl your fingers into the page here and have your fingers come out of the page down here, your thumb would point to the right. So that's the direction of the magnetic field created by this current. The flux is, or the magnetic field is increasing, so the change in flux is the same direction. To use Lenz's law to determine the direction of the electric field created at point P due to this changing magnetic field, you point your thumb in the opposite direction of the change in flux. So thumb goes right, curl your fingers. You'll see that your fingers come out of the page right there. So out of the page there, down here, the electric field would be into the page. Now I've drawn a picture of this at the right here. And that's the loop that we have right here. So at point P, this is looking at into this right end. At point P, that was coming out of the page. At point Q, you'd see, or not point Q, but down here, you'd see it's going the opposite direction. It spirals around. We've got all the little tiny DL elements that would be all around here. They're always at 0 degrees to the electric field, highly symmetric. And the electric field there is constant because we're always at the same distance away. The angle between the electric field and DL elements is 0. So when we do cosine theta, we maximize it. The area here is pi r squared. Now, this circle right here is not the solenoid. The solenoid would be bigger. It's out here somewhere. This is only to point P. From the equation sheet, mu naught little n times I is the magnetic field for a solenoid. You can also get that from Ampere's law. And of course, up here we had the middle and right side of Faraday's law. We're only thinking about magnitudes here, magnitude of the electric field. The magnetic flux through this circle is the magnetic field times the area, pi r squared. So the electric field was constant, pull that out. The integral of dl is going to be the circumference of that circle. Here is the magnetic field times the area. And so there's only one thing that changes with respect to time. That was the current. So we get di dt at the end, and mu naught nr over 2l out front. You could also write that using a little n, which would be big N over L, either way. Now for the point Q, which is above the solenoid, same deal. Flux is changing in the same direction. Point your thumb to the right, curl your fingers. You're still going to get a field out of the page here. It would still be into the page down there. The one thing that is different here is that we have only flux inside the solenoid. Outside the solenoid, in like in that section and in that section there, no flux outside the solenoid. So from the side view, we have some empty space here outside the solenoid that has no flux in it. All the flux is in the solenoid. This is now the entire solenoid with radius big R. So that's radius big R. And of course that's our magnetic field B inside there. So it's similar to what we did just above, but for the flux, the area, when we're looking at this part of it here, B times A, for A, we don't use the full area. We're going to use pi big R squared. And then this point here is at little r. And so for the electric field, we use little r, but for the flux, we use big R. That means that some of the r's won't cancel, and we get an expression which is similar to this, but instead of having the electric field increase with radius, and it increases with radius here because we're including more flux as we get bigger. Here, as we get bigger, we don't include any more flux, but we do get farther away from it. So here, the electric field decreases as you get further and further away from the solenoid. All right, on the next page, a basic inductor is a solenoid. So we're going to consider the solenoid has a certain length and coils and an area A. We want to know, what does Ampere's law predict for the magnetic field inside the loops? An expression for the magnetic flux across the entire cross-sectional area, and the EMF induced in the solenoid when the current's changing. So Ampere's law, we've done this before. You should look back in the second half of the magnetic section of your notebook where we did an example of Ampere's law for a solenoid. Put the page number in here for reference, but it's mu naught little n I or mu naught n over L I. I'm not going to go over all of that again. Magnetic flux integral of B dot dA. This is a closed integral, but it's not a closed surface. It is a surface integral, sorry, but it's not a closed surface. Actually, I'm not sure that should be there. Should it? On the actual equations here, yeah, my mistake. There should not be a closed integral there. The closed integral of B dot dA would be 0 because there is no magnetic monopoles. This should not be there. And I'll get rid of the next one as well. Magnetic field does not depend on where you're at in the area. The magnetic field is changing, but it's changing with time. And we're not integrating with respect to time here. We're integrating over the area. So the magnetic field, although it's changing with respect to time, it's not changing with respect to the surface. That means no matter where you go on the cross section, the magnetic field is the same strength at any instant in time. The integral of dA is just the area A. And plugging in what we got from Ampere's law, we get this expression for the flux. Now here again is the side view of this solenoid. There's the solenoid wire. And last time we found the electric field like inside the solenoid. We found the electric field outside the solenoid. Well, essentially what we're going to do now is find the electric field inside of the solenoid itself, inside the wires of the solenoid, where charges are free to move. And this is where we can see the effect of the electric field that's created. So for a single loop, one of these loops, you do d phi dt. The negative there is Lenz's law. That would tell you which direction it is. We don't need to worry about that right now. We're just dealing with magnitude. So the only thing that changed here with respect to time was the number, the current. So we get this, but there's n loops. This is the voltage for one loop. You got to multiply this by n, and you'll get the voltage drop across the entire solenoid, right? So I take n times the individual result, and I get this. Now, what is this saying, really? di dt, that's the change in current. So if there is no change in current, if you have just a steady current, there's no voltage drop across the solenoid. But if you have a large change in current, in fact, the larger the change in current that you have, the greater the voltage will be across the solenoid. If you're having, if you think about a resistor and a solenoid connected to a battery, if you have a larger voltage drop across the solenoid, let's say you have a 10-volt battery, a resistor, and a solenoid. Well, there's 10 volts across the battery. That means the voltage across the resistor and the solenoid have to add up to 10. So if current is steady, you have 0 volts across the solenoid, and you'd have 10 volts across the resistor. And since current is V over R, when you have more volts across the resistor, you're going to have more current. But when you start putting voltage across the solenoid, you have less current or less voltage across the resistor, and that will affect the current. When you try to change the overall voltage, because changing the voltage of the battery is what would change the current. When you try to change the voltage of the battery, instead of that voltage getting dumped across the resistor all at once, some of the voltage initially gets dumped across the inductor, and not all of it goes straight to the resistor, which is why it takes the current a little longer to get moving when you change the voltage, or to slow down. This has the effect of giving a quality of like electrical inertia to the current. Typically, current changes very quickly. You throw a switch, it's like automatically on, instantaneously nearly. But with an inductor, when you first flip the switch, you're going to have a voltage build up across the inductor, and that's going to prevent current from starting to flow as quickly as it normally would. It starts flowing, just not as quickly as it normally would. And if you had current flowing through the solenoid at a steady rate, and then you opened a switch and everything suddenly, there was no voltage, the solenoid, as the current starts to decrease, will maintain some of the voltage, and it will continue to allow current to flow for longer than it would if it wasn't there. So it's a device which does not do anything to current which flows steadily, but when the current changes, this tends to resist the change. It makes the change slower. It delays the change. Whether that's increasing the current or decreasing the current, either way, it makes it happen slower. So, more general information about inductors. Inductor is a solenoid in a circuit. Sometimes they're filled with a metal core that will enhance the effect, but we won't deal with that here. In general, inductors store energy in the form of a magnetic field if the current is flowing. Whether or not it's changing, bigger, smaller, as long as there is current, you have energy stored in an inductor. An inductor will resist changes in electrical current. If the current tries to get bigger or smaller, the inductor will delay that from happening. The equation symbol for an inductor is an L, like resistor R, capacitor C, voltage V, that type of thing. So the equation symbol is L. The circuit symbol looks like a little coil that could represent a solenoid. The voltage across a solenoid, which we just found on the previous page, was all these constants times di dt. And these constants are what make up L. which is a numerical value that you could assign to an inductor, which is a measure of how much it's going to resist changes in current. Like capacitance was kind of a measure of how much energy it can store. And it was purely a function of its physical structure, right? Think about capacitance for a parallel plate capacitor. Epsilon naught A over D, just depending on the area and distance between the plates. Well, look at it for a solenoid. What does it depend on? The number of turns and the length and the area, the size of the turns. The unit of inductance is L. The unit of inductance, which inductance is L, is the henries, H. If you find that confusing, you could get rid of that L there if you wanted to. I thought it was a good thing at one point, but I just confused myself when I was talking, so maybe it's best without it. So the unit of inductance is the Henry. A Henry is a Tesla meter squared per amp. You could break that down further into other SI units, but not something you really need to be super familiar with. I think there's probably something along those lines on the AP equation sheet. Like capacitance, it depends only on physical dimensions of the solenoid. Energy stored, 1/2 Li squared. Now, how does voltage change when you go across a solenoid? If the current is going up, the voltage will drop in the direction that the current's flowing. So you'll have higher voltage on the side where the current enters, lower voltage on the side where the current leaves. If the current is decreasing, the opposite happens. So if the current is going down, you will have a lower voltage where the current enters and a higher voltage where the current leaves. We have a little chart then comparing resistors, capacitors, and inductors. In an inductor, the voltage drop is proportional to the rate of change in the solenoid. Voltage is going to be L di dt in magnitude. And you could use this rule here to tell you if it's going to be a positive or a negative or a jump or a drop. Stores magnetic field, energy in a magnetic field. All right, we'll look at the next few examples in a separate video. See you then.